Welcome to Young Tuition. Let's continue our discussing on Veritasium's big misconception about electricity. Today, I'm going to provide an explanation for a general definition of electrical potential difference between 2 points in space. People may have not seen this form of definition if they haven't studied classical field theory. Here, I would like to thank Trevor Kearney, who drew my attention to this issue. Let's go. This is a definition by IEC, International Electrotechnical Commission. Now, you can see that the form of the potential difference is slightly different from what you've seen in your textbook if you are started doing undergraduate physics. Here you can see that the inside integral, which contains the two terms, one is E, the electrical field strength or electrical field vector. The second term involves the first derivative with respect to the time of the vector called A. Okay. Now, if you have studied the field theory of electromagnetism, and then you can immediately know that A actually is called magnetical vector potential, or magnetical vector for short. Now, how can this term appear in this definition of potential difference? Well, today, let's give you some background from perspective of classical field theory. And then I will give you a simple proof that this second term is nothing but the induced electrical field strength. Okay. Aha, this is a textbook I used during my 4th year in university a long time ago, but I can tell you, and this is very good textbook. It's written by Landau and Lifshitz. Now, from this book, you can find that will give you a lot of basic ideas involved in both classical field and the quantum field. Bear in mind, when we talk about the fields, and you must be careful because we are studying physics, right? In mathematics, we also use the concept of idea or field, okay? Where in mathematics, field, like ring, is just part of the special groups, okay, or part of a group theory. But in physics, we are dealing with real stuffs, such as gravitational interaction and electromagnetic interaction. Now, in this case, to cut the story short, we have to review that what is the basic idea in the classical theory, classical field theory of electromagnetism. The important thing in the classical field theory is that a 4-dimensional potential was introduced called A. Okay, we have subscript mu, which come from 0 to 3. So it is a 4-dimensional vector. And the first components, phi, is familiar, what we know as the electrical field potential or electrical potential for short. The other 3 components of this 4-dimensional vector is A1, A2, A3, which constituting a vector in the 3D space. Okay. So the 4 potential is the key to describe the electromagnetism in the classical field theory. But why did people bother to introduce this abstract mathematical field, okay, or called the gauge field? We mentioned that we're satisfied because A vector satisfies the gauge field. So therefore, well, today I will just outline two motives why people use this theoretical condensation. See. First, if we just use Maxwell equation, that's fine. That all electromagnetic field phenomena can be described by two vectors. One is the electrical field strength vector. Another is electric field. Another is magnetic field. And each of these two vectors requires three independent variables to describe. So therefore, basically, we have to use 6 independent variables in general cases. Now, people who study theoretical physicists are very concerned about the economy or the form of the mathematical expression. By introducing the 4 potential, we can effectively reduce the independent variable from 6 to 4. Why? Because if we just introduce this, the 4 potential, then the electrical field and the magnetic field can be written as a sum of derivative of these 4 potential. So that is the main reason. That is one reason. Of course, another reason is a bit subtle and a bit abstract for people who just begin to study at the beginning, beginners for studying the field theory. Because as I mentioned before, and by introducing so-called gauge field and some basic physics law can be considered as some kind of invariance in these theoretical fields. Okay, that is the beginning of the particle physics. Okay, I will stop here, but just remind you that the introduction of the magnetic vector is based on this mathematical beauty, and actually also these two definitions can be also considered as an alternative form or equivalent form of Maxwell equation. How? For example, from first equation, if we use a dot, we use a curve. It's called use a curve, and on both sides of equation 1, then we can obtain that the 2 terms. Now the first term by definition is that is a curve A is exactly the magnetic field. The second term, according to basic property of the vector field analysis, must be 0 because any gradients, any curve of the gradients must be 0. So therefore, the second term vanished. So we immediately obtained this the differential form of the Maxwell of the Faraday law. Okay, so why? Well, if you just do the integration on both sides in the surface. Sorry, this is F. I use F to represent the area because A is here is represent a magnetic vector. According to Stokes' theorem, and the left-hand side can be expressed as a line integral, as we see in the third equation of Maxwell's 4 equations. So that is one example that how can we rewrite Maxwell equation in a more compact form. So let's see. So that is the reason we introduce this 4 vector. Let's just go to some original description. So from the textbook, from this textbook by Landau and Leibniz, we can see that that just outline, that is where we just discussed. But it would appear there is a minus sign, and they omitted in this equation, because according to the text, according to their description, the electromotive force, that is this closed line integral, in any counter is equal to minus the time derivative of magnetic flux through the surface bounded by this counter. So therefore, this is a negative sign here, so be careful. Now, perhaps the more elegant form is this, right? So if we use four-dimensional notation, and the electromagnetic field can be simply described by these simple tensors. So F for field, and these variables have the 4 dimensions. So that is a benefit to use the four-dimensional vector. Second, it's just shown that how can we use this first derivative of A to represent the induced electric field? Here is a simplified example. Although the general relation between the magnetic field and the magnetic field vector is this equation. So B equal to curve A. But in the special case where the magnetic field is uniform everywhere, then there's a simple relation between these two vectors, namely A equal to half D cross product of R. So this just uses a diagram to illustrate this simple relation among the 3 vectors. So imagine that the uniform magnetic field is upward, perpendicular to the XY plane, as represented by this blue arrow. And you can see that this is the loop in question, and R is the vector from the center of the circle to the loop. So you can see that these 3 vectors are, the 2 vectors R and A are in the same plane, XY plane. So this diagram shows you how to use this special relation between A and B. Because in this case, and B is perpendicular to the R, so therefore we can simply use scalar form. Okay. If we just do the first derivative with respect to the time, we will obtain the dA dt will equal to R over 2 multiply dB dt. So that is interpretation of the dA dt in that general definition. Then we can just consider the same scenario, but this time we use a 2D diagram. So the same scenario, but the 2D diagram, in which I have illustrated that the direction of the magnetic field is into the page, as you can see by this cross. And it's the induced electrical field is represented by these tangent, these red arrows along the tangent direction. Okay. Obviously, and in terms of the magnitude, so this induced electrical field is the same everywhere, apart from their direction. Now, according to Faraday's law, we can simply describe this special case as this. We can work out the line integral, the loop, by using EI, the magnitude of induced electric field, multiplied 2 pi r, which is circumference, and And pi r square is the area of the circle. And this is dB, that is dB dt. So that is based on Faraday's induction law. Just in passing that you can see that the negative sign disappear because by this definition that we know that the direction of the magnetic field is the angle between the magnetic field and the direction of the area of the circle is 180 degrees. That's why the negative sign disappear. So what do we have? That is this. The induced electric field is simply equal to R over 2 multiply dB dt. Identical, see? So in conclusion, we can simply replace that dA dt by the more familiar form. It's called the induced electrical field in the definition. So that is a simple explanation of this provided by the IEC, but still it bit strange that for the ICE to invoke the four-dimensional vector in their definition, because after all, and if this guideline or standards is for the technicians, then the readers, the users would prefer to use B and E instead of A. Of course, another thing is that by using this abstract, more compact form, and the definition would appear more abstract, more theoretical physics-like. That's it. That is my simple explanation. And perhaps I will stop here, and people who are interested in studying field theory, and then I will provide more specific talks on the classical theory of field, and also what is the difference between the classical field theory and the quantum field theory. And that would be part of our talk on electricity. Thank you for watching this video. Please pick a like and subscribe. And I will continue to make a more interesting video about electricity. Goodbye.